guys, this is Professor Janacek. Let's go over some examples of improper integrals. Here we have example 3. We're integrating from 1 to infinity of 1 over x to the 4th dx. Now first off, before I try integrating, I do need to rewrite this as a limit because it is an improper integral. So I'm going to take the limit as t goes to infinity of the integral from 1 to t of 1 over x to the 4th dx. Well, if you would like, we can rewrite that integrand as x to the negative 4th dx. And in order to integrate that, notice I'm going to keep that limit notation this whole time, but now we can integrate x to the negative 4th dx is x to the negative 3rd over negative 3. Of course, we're going to evaluate this from 1 to t. Let me go ahead and simplify that a little before we evaluate it at those limits of integration. So I still have the limit as t goes to infinity. Let me go ahead and write this, though, as negative 1 over 3tx cubed. And now we'll evaluate from 1 to t. So we have the limit as t goes to infinity of negative 1 over 3t cubed minus negative 1 over 3 times 1 cubed. Well, actually we can go ahead, I don't need this. Let's go ahead and take this limit. As t gets really large here in the denominator, so again, the denominator is getting very, very large. That means that whole fraction is going to 0. Now we don't have any t's here, so we can just evaluate that second term as is. So the first term goes to 0. The second term goes to 1/3. So we end up with just 1/3. All right, there we go. Let's take a look at the second example. It's actually somewhat similar. We're integrating from 1 to infinity of 1 over x raised to the p power of dx times dx. So we have an exponent of p. Let's do the same thing. So it's following the same rules as we saw in example 3. We're going to take the limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx. Again, let's go ahead and write this as an exponent not in the denominator. So our integrand becomes x to the negative p dx. And if we integrate x to the negative p dx, let's go ahead and integrate that. That gives us x to the negative p plus 1 over negative p plus 1. And now we're evaluating that from 1 to t. Well, before evaluating it, again, I want to go ahead and clean this up just a little bit. I'm going to write this numerator, x to the negative p plus 1. I'm going to factor out a negative from that numerator. So it's going to, from that exponent. So it's x to the negative times p minus 1. And then in the denominator, I'm going to just turn it around. Instead of negative p plus 1, I'll write it as 1 minus p. Okay, so now that I have this written as kind of a negative exponent, I'm going to go ahead and write that, move that to the denominator. So we'll write it as the limit as t goes to infinity of 1 over 1 minus p times x to the positive p minus 1. Still evaluated from 1 to t. So notice what I did there. Instead of taking this negative here in the numerator, I put it down in the denominator, but now it has, quote, a positive exponent. We really don't know if it's a positive or negative, but I can write it as a positive p minus 1. Okay, so now let's go ahead and try to evaluate that and see what we get. So this is the limit as t goes to infinity of 1 over 1 minus p times t to the p minus 1 minus 1 over 1 minus p times 1 raised to the p minus 1. Well, let's see what's going on here. Well, t is getting really large, and so that means the denominator is getting really large, which means this whole fraction is getting really small. So that first part is going to 0. However, this second part, and actually we don't even need to write this, the second part, what's going on with that? Well, 1 raised to any power is still 1, and so what we end up with is 1 over 1 minus p. Of course, that's, actually, let's go ahead and write that. Let me show you. So we get 0 minus 1 over 1 minus p, which we could write as, let me take this negative and distribute it, but I'm going to distribute into the denominator, which gives us 1 over p minus 1. Now, this is only true for p greater than 1. It turns out that when p is less than or equal to 1, this diverges. And so this is actually a really nice result. In fact, it's we could use this back on example 3. If we take a look at example 3, we're integrating from 1 to infinity of 1 over x to the 4th dx. In this case, our p is 4, which of course we see p being 4 is definitely greater than 1. And so we should end up with 1 over p minus 1. So that would be 1 over 4 minus 1, which is exactly what we got. 1 over 4 minus 1 is 1/3. So it worked for example 3 quite nicely. So it's a nice little rule whenever you're integrating from 1 to infinity of 1 over x to the p dx. You can actually kind of now just skip through all this craziness and go straight to this as long as p is greater than 1. If p is less than or equal to 1, then we'll say that it diverges. All right, let's take a look at example 5 here. We're going to integrate from 1 to 10 of 1 over x minus 2 raised to the 1/3 dx. Note on this one that there is a discontinuity at x equal to 2, because that would make our denominator 0, so there's a problem there. So, and of course 2 is within our interval of integration. It's between 1 and 10. So how do we deal with that? Well, we will set this up as 2 different integrals. We're going to integrate from 1 to 2, plus the integral from 2 to 10. And each of those integrals needs to be written as a limit. Now we need to be careful because that 2 is an endpoint now, so we'll have to approach it from within the interval on each time, on each one of these limits. So this first limit, we'll take the limit as a goes to 2, but it needs to be from inside the interval, so from the left-hand side. And then we're going to take the integral from 1 to a. The second one, we'll take the limit as b goes to 2, but from the right-hand side, oh, and let me clear up this notation here. Again, it has to be from within our interval that works. So from 2 to 10, that's going to have to be from the right-hand side. Just like this one from 1 to 2 was from the left-hand side. And this second one, we integrate from b to 10. All right, now how in the world do we work with these integrals? Well, again, if you want to rewrite them, it's not a requirement, but let me go ahead and take a moment and rewrite this integrand as x minus 2 to the negative 1/3 power This will require a u substitution, but a very simple one. If we let u equal to x minus 2, then du is simply dx. And we are integrating, in both cases, u to the 1/3 power. Oops, actually it's to the negative 1/3 power, and I left one of those off. That should be a negative 1/3. There we go. Integrating u to the negative 1/3 du, which gives us 3/2 u to the 2/3. So that's what we're going to use on each of those. I'm not actually going to rewrite this in terms of u's. I will keep it in terms of x's. So we integrate the first one. That gives us, keeping that limit notation there in the front, 3/2 times x minus 2 to the 2/3 evaluated from 1 to a. The second one, again, keep that limit notation on there. We get 3/2 times x minus 2 to the 2/3. This one gets evaluated from b to 10. Right, so we'll go ahead and evaluate each of these. At those limits of integration. Do the same for the second one. I think we can simplify this just a little, but let's go ahead and while we're simplifying, we can also evaluate those limits. So a is getting very close to 2, and that means as a gets close to 2, well, let's just take a look. A gets close to 2, that's going to get that a minus 2 gets close to 0. 0 raised to some power or multiplied by a coefficient, all 0. So this first bit becomes just 0. Now this next little bit, take a look at that. We have 1 minus 2, which is a 1. Raise that to the 2/3 power, gives us still 1 times negative 3/2. Looks like that gives us negative 3/2. Okay, for the second one, here we have 10 minus 2, which is 8, raised to the 2/3. Now, I'm going to take the 1/3 power first, so that's the cube root of 8, which is 2, then square it, which gives us 4, then multiply by the 3/2. Looks like that gives us What would that be? We say 4/6 halves? No. Is that just a 3? That's just a 3. And then this last little bit, as b goes to 2, that gives us a 0 in there, so this whole piece goes to 0. Oh, wait, and that actually goes to 6. What am I thinking? There we go. That's looking better. All right, so we end up with -3/2 plus 6. Get a common denominator there, which I think would be 2. And that ends up being 9/2. And there we go. All right, enjoy.